Good morning, everybody. Welcome to our workshop number 12. This time we have the pleasure to have the ION group showing us the talk titled Offshore Colombia Highlights of Prospectivity Margin Segments Using Newly Reprocessed 2D Seismic Data. Okay, just to remind you on this slide, the talks that we will have in the rest of the month. Next week, we're going to have the Geological Survey of Colombia, talking about the thermal history of exhumation of the Garzón Massif and the evolution of the Caguán-Putumayo Basin. On May 20th, we will have as well the Colombian Geological Survey, talking about the Colombian Caribbean Plate fairways. And the last talk on May 27, will be given by the ANH, and that will be the seismic interpretation in areas reserved by the ANH. We will discuss specifically the area in the Sinu San Jacinto area, Repelón. We will talk about some opportunities in the Putumayo Basin, in Las Águilas, in the place called Las Águilas, and we will discuss some aspect of the heavy oil in the Llanos Basin, El Miedo specifically. As you can see in this slide, so we have covered more than 24 areas that we have proposed to you to be nominated. So for people new in this talk, people new in this conference, we have opportunities for gas and condensate, light oil, medium oil, and heavy oil. So don't hesitate to contact us and all access our website to see all those opportunities individually. We can organize as well data rooms and for your knowledge. Don't forget that we also work on the gas transition fuel purpose for Colombia. And beside those talks on May on gas in the Caribbean, in June, we will have this interesting talk on June 13, organized by MinCiencias. And this is titled Geological Habitat, Prospectivity, Socio-Environmental and Economic Sustainability of Wet Gas, LPG, in Colombia as an energy transition fuel. And in July 8, we'll have as well a very interesting talk regarding the Eastern Cordillera of Colombia for conventional and unconventional gas reserves, and that is and prospective resources. And the title of the talk is Giant Gas Potential in Cretaceous Rocks Along the Eastern Cordillera of Colombia. Well, we have today a couple of very interesting people that work for ION. And we have the pleasure to have Dr. Kyle Reuber. He's a PhD, he's a geologist for ION team based in Houston. His primary area of focus is Latin America and the Caribbean. Kyle's remit primarily consists on designing ION span programs and regional interpretation projects that integrate the regional 2D span and available reprocessed vintages datasets. Kyle earns his Bachelor of Science degree in geology from Wright State University and a PhD from the University of Houston. We have also the pleasure to have Dr. Antara Goswami. She's a senior geologist for ION Geophysical Corporation. She received her bachelor degree in geology from the University of Pune in India and her professional master's degree in geology from the Rice University in the States. She has worked in several 2D and 3D programs in the USA, Canada, and Central America. She has led interpretation and integration teams on regional projects in the GOM, offshore Panama, and Colombia in the Caribbean Sea and the Pacific coast of Central America. So we will have Antara as a first speaker, and welcome Antara and Ken.
Thank you for your kind introduction, Miguel. I'm going to start sharing my screen now. I hope everyone can see my screen. Good morning, everyone. Welcome to the ANH webinar series. Our talk is called Offshore Colombia, Highlights of Prospective Margin Sediments Using Newly Reprocessed 2D Seismic Data. I will be presenting the first part, which is about the South Caribbean Deformed Belt, and then I will hand it over to my colleague, Dr. Kyle Ruber, and he will be presenting the second part on the deep water and the ultra deep water. So I'm going to go into presentation mode and I'm going to stop my video so it doesn't interfere. To get my laser pointer. I hope everyone can still see my screen. So here's a quick agenda for my part of the discussion. I will start with an introduction slide, and then I will talk about a little bit about the data set. I'll give examples from the legacy data, show some sections of our regional velocity and gravity models, and then show some examples from the offshore composite lines. And then I will talk about the different areas within the deformed belt, starting from the Sinu offshore, Magdalena Delta, and the Guajira offshore. And I'll be showing examples from the seismic data, velocity, and AVO, and also discuss possibilities for hydrocarbon exploration. And then I will hand it over to Kyle, and he will talk about the deep water and the ultra deep water. So this is my introduction slide. This slide shows the data set that we've used in this project. So in this talk, we are primarily talking about the Columbia repro or the reprocessing data set. This covers almost 60,000 line kilometers in offshore Colombia. So this consists of 18 different surveys of different vintages. So as you can see from the different colors on the map, and all of these have been reprocessed together. We've also used 13 wells in this project for the velocity model building as well as for interpretation. So this kind of an extensive coverage allows us to compare structural styles on a regional basis using adjacent data sets like, for example, the Panama span data. And then we also have the basin-wide lines from Antilles span. You will also see that we have a denser survey grid within the areas of the deformed belt. And this makes it possible to do a more detailed analysis on the variations of structural style in adjacent areas like the Sinu offshore, Mag Delta, and the Guajira offshore. And then there is this larger grid out in the ultra deep water. And this allows us to map large scale features such as crustal thickness. So we map this area of thin oceanic crust, and we're currently analyzing the interaction of the thin crust with the deformed belt. So now I will move on to show you examples from the legacy dataset. So this is the legacy version of an east-west strike line, and this is out from the ultra deep water. This is not a very old data. I think this is from 2012, but we have much older data sets like from the 1980s. So this is the Saguay in the state that we received it. And I admit that we could have put some kind of an AGC or some low-level processing to bring out some events, but we wanted to show you what the starting point for this project was. So this is the image prior to any filters or processing being applied. So you can see from this image that it looks pretty opaque and washed out, especially in the deeper sections. So this was the old, and this is the reprocessed data. Let me flip back and forth once more. Old, new. So now you can see the dramatic uplift in the crustal events. You can see a clear moho and a number of intracrustal reflectors. We also see a very good uplift in the deformed belt in the sedimentary sections as well. So these kinds of improvements in imaging have allowed us to review and build on past interpretations and tectonic models and open up discussions like the one that we're having right now about the tectonic evolution in this area. So now I'll move on to show you some examples from our regional velocity and gravity models. As I had mentioned before, all 60,000 line kilometers of data have been reprocessed as a single project. And this allows us to create these unique basin-wide 3D velocity and gravity models. For the velocity model, we have incorporated the well data from the 13 wells to constrain the imaging and tomography. And this is especially helpful in areas of very complex geology. The advantage of having a regional model like this one is that you're able to create a transect in any direction, any shape that you want. So I'm showing this transect, and it doesn't really fall on any particular seismic line, but it goes all the way from Urabá, the Urabá Basin in the west, through the Sinu offshore in the Magdalena Delta, and then the line comes close to the coastline where you can see the Santa Marta Massif and the basin high associated with it. And then the line goes further east into the offshore Guajira area. So similar transects in areas of limited data or well coverage can provide us with an initial framework or a starting point in case there's no other data coverage nearby. And the other thing I would like to mention is that we always try and preserve the detail that we see from the passes of tomography into our data. For example, you can see these low velocity, I'm sorry, I think my laser pointer is stuck. You can see these low velocity anomalies out in the Sinu offshore. Then you see the sediment detail within the Magdalena Delta package. And all of that is preserved throughout this line. So similar to the regional velocity model, we also have the gravity transects. So these are, we're showing two examples here, one from the Sinu area and the other from the Magdalena Delta area. The gravity models are built from shipborne data wherever available, and then they're supplemented by satellite data and any global databases that are available to make the entire gravity model. So here, this is especially helpful in this kind of a project because although on most of the lines we can image basement quite clearly, there are some lines which lack the record length, especially for the older data sets to image all the way down to the moho. So then having a gravity model, a regional gravity model like this one really helps constrain and guide our interpretation and our velocity model building process. If you look at the two transects here to the right, you can see that they're in pretty good agreement with the observed and calculated gravity. And you can also see the crustal variations in the thickness of the crust when it comes to the Sinu offshore and then the Magdalena dip line over here. So this is the area of thin crust. Two more examples. Now this is a dip line from the Guajira offshore, and then there's a deep water tie line, which is a strike line. So again, pretty good agreement between the observed and calculated gravities on both of the lines. And you can see, again, the crustal variation in the deep water line. So this is the kind of information that is integrated into the velocity model building. And it iterates with the geologic interpretation to make a more robust and geologically sound product. So next, I'm going to show you a couple of examples from the regional composite lines. This first one that I'm showing you is from the ultra deep water, and it shows this beautiful example of the variation of thickness in the Caribbean Large Igneous Province, or CLIP. So you can see that a zone of thin crust, which is seen here in this section, that has been mapped out in the ultra deep water in the Columbia Repro dataset. And this is in like stark contrast with the adjacent crust nearby. For example, the oceanic crust in Panama reaches almost 15 kilometers, and the one right next to it is almost 2.8 kilometer. So I'm not going to go too much into detail here because this is the primary topic of discussion for part 2 of our talk presented by Kyle. But to be very brief, the CLIP is the anomalously thick buoyant plateau crust that is currently subducting under South America in an east-southeast direction. The initial subduction of the Proto-Caribbean crust started in the Cretaceous, and this was the normal thickness oceanic crust, which was accompanied by the usual arc magmatism. And this was followed by the subduction of the plateau crust. The onset of the low angle oblique subduction of the CLIP occurred during the lower to mid Eocene, and it coincided with the simultaneous ending of arc magmatism, and also a change in the plate angle as well as velocity. So my second composite line, this regional composite line, goes through the deformed belt area. And the section with the thin oceanic crust is outlined here in this red box. So this profile gives us a clear picture of two elements, depth to basement and the sediment thickness. So you can see that the section of thinned crust here in this red box coincides with a basement low in the offshore Bahia area and in the Guajira area of the deformed belt. And it is in the middle of a zone of high sedimentation and very thick sediment loading. So the Mag Delta in this section reaches almost 9 kilometers in thickness. And out here in the deformed belt, the sediments are almost 12 kilometers in offshore Guajira. I think Paul Mann had also presented this observation in one of the APG webinars, and it coincides with what we see in several of our lines in the dataset. So now I'm going to go through the different offshore areas, and I'll go from west to east. I'll start over here with the Sinu offshore area. The Sinu fold belt This is an accretionary wedge, which is formed in response to the oblique convergence of the Caribbean plate with South America. This accretionary wedge consists of the Sinu fold belt, which is the offshore active portion of the accretionary prism, and the San Jacinto fold belt, which is the onshore fossilized prism, which acts as a dynamic backstop along with the outer high. And there is another static backstop, which is further inland. The Sinu accretionary prism is underlain by thick Caribbean plateau crust. And I've been reading some papers. Rodriguez and his team have been publishing some excellent work on the structural mapping of this area. And a lot of his observations are confirmed in our data set as well. So we have studied the toe thrusts in the area, especially because of the giant gas discoveries seen in these kinds of structures. And then we also found a small area where the frontal toe thrusts in the central section change vergence from seaward to landward. And this is perhaps in response to the increased sediment thickness. And also there is a distinct change when we go in a strike direction. There's a change from the highly deformed fold belt of the Sinu prism to the undeformed Magdalena sediments to the east. So let's look at some data examples. This first example is a dip section, and this is from the southern side of the Sinu fold belt. This again, you can see is underlain by the thick plateau crust, and it displays low rugosity in this area. And you can see some beautiful like linear flows close to the basement. In this section, the accretionary prism reaches almost 10 kilometers in thickness, and mostly seaward verging faults within the body of the prism. The main décollement seems to be pretty close to the basement, but we can see some shallower décollements on the shelf where the mud diapirs are located. And we see a pretty good BSR running through the prism. It's pretty mappable. And then for this particular line, the toe of the prism, this structure is where the Gorgon well was drilled. The well itself is a little further south of this line, but it's essentially the same structure. So I wanted to point that out. And then the other thing about this section is that you see we've mapped several MTCs further down dip in the sediment section, down dip of the toe. And a lot of these MTCs have been incorporated into this, excuse me, toe thrust structure. The second data example is a line from the central section. And this is something that I wanted to use to show you the contrast between the toe thrust structures. So this is located in this area where the prism almost, in map view, the prism almost appears to bulge out. The sediment thickness on this line reaches close to 12 kilometers in this area. And, oh, excuse me. Excuse me, I think I got disconnected for a little bit. Can everyone still see my screen?
Yes.
No, Tara. Yep.
Oh,
Yep, we have you.
Okay, I'm going to, let me see if I can.
Tara, we can see it. It's on the slide that says dip section through the southern Sinu.
Okay, sorry. I think I have a lag here. So I'm going to go back into slideshow mode. Sorry about that, everyone. All right, can you still see my screen?
We can see it's the same slide still. It didn't change.
Oh, that's fine. I think I was, can you see my pointer?
I cannot.
Okay. Sorry about that. Can you see it now?
No, nothing's changed.
Okay, let me advance to the next slide.
Yeah, you might have to stop sharing and then try re-sharing again.
Okay, let me do that.
Okay, we can see the PowerPoint window.
Perfect. Let me
And now
go.
No presentation mode. We can see your pointer.
Perfect.
Yes.
Okay. Thank you. Sorry about that, everyone. So let me see, where was I? Oh yes, I was talking about the sediment thickness in this area. So now this is from the central portion of the prism, where it bulges out in map view. And here is where we see the lines have greater sediment thickness as compared to the lines to the south and to the northeast of them. Again, the shelf area in this section shows a higher density of shale structures and extensional faulting. We see a prominent BSR going through the prism. And here, the landward vergence of the toe thrust that we see on this line is only exclusive to these lines within the center. And they seem to abruptly end at this fault, which you can see on map view. It's the Rosario fault. So these landward thrusts on our data seem to be on a separate detachment surface compared to the seaward verging thrusts, which are inside the prism. But when we compare them to the lines which are nearby, these landward verging structures seem to be larger than the seaward verging structures on adjacent line. The seaward verging structures have more closer faulting, so the individual structures appear to be smaller than the ones in the landward verging direction. This next data example is the strike section through the Sinu prism. And this is a very interesting line for a lot of reasons, but I will start with the mud diapir over here. So you can see a prominent mud diapir here on the left side, and it reaches the surface. And then there are several levels of thrust faulted structures. And this line has several detachments in the strike view running through the line. And you can see that there's a very clear reflection of the basement and a lot of linear features right underneath the basement, like we've seen on the dip lines as well. But what's more interesting about this example is its velocity section. So I'm going to show the velocity overlay. So you will immediately notice that this is not your regular velocity section with a nice smooth gradient down to the basement. There are several zones of inversions ranging from shallow, like this mud diapir, to the deep. So in the sediment section, one of the most prominent inversions is the one with the mud diapir, where you can see the slow velocities continue on towards the base. Now, this deeper inversion is something that we've consistently identified during velocity model building. It's mapped over a fairly sizable corner of the Sinu prism, and it's been tested and analyzed several times. So this could indicate a zone of décollement or a pressure variation, and this could have implications for migration pathways in the area. So I've shown you this velocity example, and I would like to show you an AVO example from the Sinu area. But before I show you that, let me talk a little bit about the AVO methodology that we've been using. So AVO attributes, we are using this calculation of far stack minus near stack multiplied by the far stack, which is a rough estimate of an AVO gradient, particularly for the class 2 and class 3 AVO anomalies. This is taken from the paper by Davidson using data in Southeast Somalia. So this is the same calculation that we've been using to calculate the AVO attributes that we'll be showing you in this paper. Some pitfalls, and this is something that Chi Hong from our team had pointed out when we started this work, is that first of all, trace balance data tends to boost the difference. And the FARs in the volumes, the FAR volume has lower frequency than the nears in our data set. So we have to keep that in mind when we're looking at the AVO examples. So the line that I've chosen goes close to Gorgon. It's not directly on it, but it's close to it. And you can see this is just the final PSDM stack. And you can already see the bright amplitudes on the flanks down dip of the main structure. You can also see something of a flat spot close to the reservoir level. So this is final PSDM stack. And these are the nears, so 5 to 15 degrees. And these are the fars, 35 to 45. I'm going to flip back and forth between the nears and the fars. Nears, fars, nears, fars, And next is the AVO attribute calculation. So you can see the brights on this image are kind of congregated within the same within the layers, which could be identified as the reservoir levels throughout the structure as well. And then you have some shallower anomalies closer to where we map the BSR up in the prism. And then this is the accompanying interval velocity for that PSDM data set. And the reason I wanted to show you this is that we were trying to see if we could expect a velocity anomaly as well, where we see the AVO, the bright amplitudes on the AVOs. But we were not able to, we played around with the interval velocity ranges, but we were not able to find a clear velocity anomaly for the structure. So last point about this area is a discussion about the hydrocarbon exploration. The Sinu fold belt itself is pretty active in terms of hydrocarbon exploration because the giant gas accumulations at Gorgon, Purple Angel, and Kronos are all located within the toe structures within the prism. So I've given the example of Gorgon here, and I pointed out that there was a distinct flat spot at the reservoir level. And this is the reason why mapping these individual structures is very important, and having a closed grid like the one in our project. It's very important to establish volumes and lateral continuity, and this kind of mapping is going to help in doing that. There are these the new geochemical analysis that suggests that the dry gas accumulations in these fields contain a mixture of microbial and thermogenic gases. And the most likely source rocks in the basin are could be from the Oligocene to early Miocene. Further onshore, the Upper Cretaceous Canzona Formation might be sourcing the seeps in the San Jacinto belt. Then we also have the presence of the continuous decollement surfaces, which could facilitate migration from if there is a deeper kitchen further inboard within the prism. And again, there's a strong BSR that's been mapped within the fold belt. So you've seen examples of several trap types already in the dip sections and the data examples that I've already showed you. For example, thrust and related folds, extensional structures up dip on the shelf, and any mud diapirs and related pinch outs. So now we'll move from the Sinu area onto the Magdalena section. So this line is a strike section. Moving east from Sinu fold belt into the mag fan, and then back into the deformed belt in the Guajira offshore. So before we talk about the deformation, I would just like to point out the basement on this strike line shows some beautiful dipping features, and they seem to disappear as we go into the east and we enter the region of the thin crust. So the deformation of the Sinu fold belt seems to kind of abruptly stop as we cross the Galarazamba fault as described in the Galindo paper. And then we enter the undeformed section of the mag sediment pile. Then as we move east, so east of the fan, we can see the deformed belt pick up again. And here in this area, it's almost aligned in a north-south axis. And also interestingly, I mean, you can see the different fan and delta features out here in the Magdalena fan. We can also see some of their MTCs, some of the larger MTCs and the smaller ones. They can be tracked into the structures, the compressional structures on either side of the Magdalena fan. So a little quick intro about the Magdalena delta and fan. The fan deposition started in the late Miocene on the pre-existing accretionary wedge at the time. There's almost a sediment pile which is about 12 kilometers thick and underlain by the Caribbean plateau crust, and at some places by the thin crust. The fan itself has been deposited on an active margin, but it appears to be itself largely undeformed. And the high sediment supply may have induced collapse of any pre-existing compressional structures. It exhibits all the classic examples of a channel and fan system. A lot of channel levee complexes. We use this zoom in from this picture, and Kyle and I were looking at this yesterday, and we counted almost 20 CLCs within just this one little zoom. We see several erosional features, and then we've mapped a number of MTCs in this project. Some of the MTCs are really extensive, and I think the largest one that we've mapped is all close to 60,000 square kilometers. So multiple deep water trap types, which could be related to the fan system, including nested channels, levees, MTDs, turbidite complexes, base of slope fans, etc. We've seen several areas in our data set where the sediment section thickness is more than 11 kilometers. So it's definitely good news for any deeper located source rocks in this area. The piston core and soil sample geochemistry at seep sites supported thermogenic systems. So there is a possibility for any kind of thermogenic gas, wet gas, or liquids in this area. There's also been an untested oil play, which has been proposed, sourced from the Upper Cretaceous to Paleocene marine restricted shales. So moving on from the Magdalena, now onto the offshore Guajira. The offshore Guajira, this is the eastern limb of the South Caribbean deformed belt in Colombia. The fold belt itself changes orientation from north-south in the west to almost east-west in its northern limit. And this is a relatively narrow accretionary fold belt, especially if you compare it with something like the Sinu. And this could have something to do with the fact that the static backstops, which are the continental blocks, are present offshore. So they're much closer to the accretionary prism. And then you have these broad basins like the Tayrona Basin lying in between the backstops and the accretionary prism. Tayrona lies within the boundary of the thin oceanic crust that we had mapped from the ultra deep water. And the Chamari subbasin lies on the plateau crust. So the suture between them seems to almost line up with the eastern limit of the thin oceanic crust that we've mapped. And in the seismic section, again, you can see the basement is still deepening as we go underneath the Guajira deformed belt. And you can see a very abrupt transition from the undeformed fan sediments to where it meets the compressional structures of the deformed belt. So the data example from this area, I'm going to start with the dip section through the Tayrona Basin. So this is underlain by excuse me. This area lies on the thinned rugose oceanic crust, as we had mapped from the deep water. The accretionary prism here is much narrower than the Sinu fold belt in the west. And again, that might be related to its proximity to the static backstops. The prism itself has several seaward verging faults, mostly, and multiple decolman levels can be mapped within the prism. Just north of the prism in the toe section, we see some faulting in the incoming sediment section. If you observe the faults on adjacent lines, they have a tendency of becoming more landward verging as we move towards the east, towards Chamari. Then there is the shallow section, which consists of neogene to recent sediments. And we have mapped several unconformities. Some of them are very clear within this sediment section as well, this seismic section as well. And all of them are within the Miocene section. And lastly, there is a very prominent BSR running through the entirety of the prism. This next data example is a strike section through the Tayrona Basin. And I wanted to show you this line in particular because this area shows the extensional features within the basement. Block faulting is seen in some parts of Tayrona as well as in the Chamari subbasin. And they're indicative of a rifting event, possibly within the Jurassic. The exact timing of the rifting is still uncertain. If it is Jurassic, then the grab and fill could contain the that elusive Cretaceous source rock, which could drive a thermogenic hydrocarbon system. This line also contains some interesting features in the shallow section. So I am going to zoom into these features. So going from west to east in this line, we see a mud diapir that breaks the surface along with a BSR. And then there are some bright amplitudes on the flanks of the diapir as well. Then we move on to the central section. This section is full of DHIs. We also see a BSR running throughout the system. And then we see bright amplitudes within the sediment section as well. There are some channel features, and we can see some bright amplitudes at pinch outs. And these also light up when we do our AVO analysis. And then moving on towards the flanks of the structural high, you will notice this collection of bright amplitudes, and these are pretty close to the BSR. There could be faults connecting it to the grab and fill directly, or it could have migrated up dip from maybe someplace down here. So now I'll move on to the AVO examples from the Tayrona area. So first, this is another strike line in the Tayrona in the Tayrona basin itself. It's pretty similar to what I had shown you before, but now we have some interesting features within the basin itself. Again, you will see the mud diapirs breaking the surface out here. So this is the final PSDM stack. These are the nears, 5 to 15 degrees, and the fars. Nears, fars, nears, fars. So there are some areas, especially in this section right here, where you can see some bright events on the flanks, in the deeper section as well as in the shallower section. As usual, the area near the BSR lights up quite well. And this is the AVO attribute calculation. Again, you can see some bright amplitudes on the flanks of this structure and some shallower areas as well as the bright amplitudes following the BSR. And this is the velocity section. Now, this is quite interesting. Again, a lot of inversions within this section. The presence of interbedded Oligocene mud and diapirs is quite well known in the Tayrona Basin. And they generally manifest as these kind of like slow velocity anomalies. So like the ones in blue and green, and then some shallower ones up here, closer to the shallow mud diapirs as well. And the velocity modeling in this area has helped us to identify the shale sections that at some places look like normal sediment on seismic. So the presence of mobile shale has in this area has another important effect, which is the creation of traps. Shale movement and escape creates the possibility of four-way anticlinal traps and also broad folds, turtle structures, pinch outs. So it's very important in terms of trap generation. This is the second AVO example from this area. So this is the final PSDM stack. So this is a strike line, but it's from the very eastern corner of the offshore Guajira area. And I chose this line because it has some interesting features on it. It has a row of diapirs on it, and it has another structure, which is also probably influenced by shale movement. So this is the final PSDM. The nears, 5 to 15 degrees. And the fars. Nears, fars, nears, fars. So there are some areas that do light up, like for example, this structure over here. And a lot of the areas along the flanks of these diapirs also light up really well. This is the AVO attribute calculation. And again, you can see the brights over here on this structure along the flanks of the diapir. And a lot of these shallow sediments seem to show up very bright on our AVO analysis. And these are the corresponding velocities. And we can see a number of low velocity anomalies along where we saw our bright amplitudes, as well as the bright areas on the AVO analysis. Okay, so this is my last slide. This is the discussion for the hydrocarbon exploration in this area. I've shown examples of multiple trap types on the previous slides. We've looked at structures related to shale movement and grab and fill in the rifted section in Tayrona. There were the compressional structures of the deformed belt itself. But here is another example. This is a nice example of an imbricate thrust faulted structure that incorporates an MTC within it. And there's another province that I haven't mentioned yet for trap types in offshore Guajira. We've observed some flat spots and DHIs in the incipient folds down dip of the deformed belt. I think Paul Mann had presented on this topic as well. We see several of these examples in our data set, but I won't go into detail because Kyle will be presenting some AVO examples in his talk about the deep water areas, because these fall within the deep water section. So the presence of a thermogenic system has long been speculated in this area, and now especially there is an increasing evidence that the giant gas fields like Chuchupa and Baena do display a thermogenic component, and the presence of thermogenic hydrocarbons in piston cores has been already confirmed in offshore Guajira. So it looks like the presence of dry gas or wet gas or liquids which are have a thermogenic origin could be a possibility in some of the structures that we're seeing in this area. So that is the end of my section. Apologies for the interruption. I'm going to hand it over to Kyle to present his half of the discussion.
Thanks, Antara. I'll get set up here. Can everyone see my screen?
Yes.
Yes.
Okay. All right, so Antara covered essentially the margin segments that are in the south or closer to the onshore regions. And what I'll do now is we'll focus on primarily the deep water area, Colombia, to the north of those. So just the structure of this portion of the talk, I'll go through the previous work, some work that Antara and I had done back in 2019, some general observations of what we see, in the data, a discussion section of how we interpret what we see, and then I'll move into an AVO analysis, and I'll use that same AVO attribute that Antara used in some of the previous slides, and we'll look at some of the blinkies and the DHIs that we think we see in the deep water, and then finally just a wrap up between Antara and I. So previous work. This is a slide from what Antara and I presented in 2019 at a GeoGolf presentation, and what we identified was, using the Antilles data, was this area of what we thought was thin crust. And at the time I thought it was, well, that if I correlate with what I see in seismic to what I see in this filtered magnetics data, is that I think maybe this is an axis of thinning. The plus signs indicate areas where we see intrusions, so the little bit higher density in the areas south of Hispaniola, and what we thought was kind of this magmatic pile in the area south of Hispaniola. This is the Beata Ridge in Panama, and we'll see a slide that shows it. We see an area of spreading that's something similar to what we see in the South Atlantic, where we have conjugate trains of SDRs. And then finally, this is kind of a basement high that separates the basins of Colombia and Panama. So this is a slide from that talk, and what we've seen recently published by Garcia, Reyes, and Diamond last year was that they used marine magnetics to also interpret a region of spreading with an axis that they date back to the Cretaceous time. And they also would have placed the spreading to have occurred when it was in the Pacific. So that was encouraging to see, as kind of it supported what we think we saw off of our couple of Antilles lines. But now that we've worked with some of the data in the deep water areas of Colombia, we can constrain it a little bit better when we use the data and also work with some of the filtered gravity and magnetics. We've placed this polygon outlined in white, which really kind of defines the area which we think it moves from a plateau thickness of crust to an area of thin crust. And it's bounded by these areas of what looks to be extensional features that kind of flank this entire area. But what we're having difficulty, and the data kind of limits constraining it, is how that portion of the plate enters into the fold belt. We've got a couple of lines we can see going in, but how does that correspond, and how does that interact with the overriding South American plate? And that's these data in the south, the higher density grids here, they tend to have they're older for one, but they tend to have a little shallower data record, and we can't see into the deep for the majority of how it enters into the fold belt here. So this area, I don't know why it's doing that. This area, this totals about 80,000 square kilometers of what you would see is not plateau crust, but rather a thin kind of oceanic crust. So now moving into observations, this is a line from the deep water, and I was asked the other day on a talk that I gave, I said, well, how do you know it's moho? And the image on to the right shows a really well imaged moho. This is near the Hess Escarpment, and we can map it. I mean, I guess that's the most simplest terms of why is we're confident this the moho is because we can map it and we can make a coherent map that matches with what we see in the basement topography. So generally, as the basement tends to deepen, the moho tends to shallow. That's just the relationship between the moho and the basement for generally most settings from an isostatic explanation. So this is a composite line that extends through this area of thin crust, and I've highlighted some of what we see on both sides and then in the center as well. So I think on outside of that area, that yellow polygon, we certainly see the typical and what you'd expect, that Caribbean plateau or parts of the clip. In the east, you can see the multi-generational flows of magmatic events, I would say, on the Beata Ridge. There's a big seamount. And then through this area, and these seamounts they disrupt the image of the moho fairly consistently. But we can track it on both sides, and you could, if you step back and get kind of these regional views, you can map the moho pretty well. So it tends to shallow here, and then the basement tends to deepen as well. You enter into this area of thin rugose topped oceanic crust that then transitions when you come out of it to the west, and then it goes to the thicker plateau crust again. And then this area is also kind of ringed with these packages of dipping reflectors. And we'll zoom in on those on the next slide. So on both sides, to the east and west, you can see these dipping events, which I would interpret as seaward dipping reflectors, but this is what Planck in 2010 would have called the inner SDRs, where they're magmatic flows, but they fill those initial sets of half grabens during crustal thinning and right before crustal rupture. So again, these kind of flank this area of crust around it on either side. And we can map these, and there are all these lines, and it's very helpful to have the data that extend through here. You can see them. It's a consistent feature around that area. So I would interpret that as, during the initial stages of this spreading, as there would have been a shortened period of magmatism, similar to what you see again in the South Atlantic or other volcanic margins. But then as we enter into the area of thin crust, it seems to be amagmatic. We don't see the training SDRs that you see on other volcanic margins. And I understand this is kind of a unique thing, that you would have crustal rupture of an existing oceanic volcanic plateau in the Caribbean, the clip. But I think we can establish that it does occur because we see it also in Panama, and we'll see that on a coming slide. But for this area of Colombia, we can map this essentially very thin, 3 kilometer thick section of rough top or rugose top oceanic crust. It's overlaying anywhere from 4.5 to even sometimes some of the deeper sections, it actually goes to 6, but rather 6 thick sections of sediment. So if we move on to the discussion section of this talk, this is a time section that extends from the ODP 999 well across the basin to 153. And these are important data points because what they do is they establish the ages of the sediments on these basement highs. Here you have, this is the Imbrara Hills, or I guess the Kogi Rise is what the 999 was drilled on. And then 153 is the section of kind of thicker plateau crust that as it enters into the South Caribbean deformed belt. So the question is how do you get such a high variability in your basement? Well, I saw this seismic character or seismic signature. I said, there's got to be some place on Earth if someone's published a similar similar setting, if you will. And what I found was, this is a paper published by Lutz in 2018 from the Nansen Basin out in the Barents Sea. So the Gackel spreading ridge is an ultra slow spreading ridge, 2 centimeters a year, that's been dredged, and it's been dredged and it's been determined that it has serpentinized periddotites on it. So basically, they've unroofed the mantle through a slow amagmatic spreading center, and it's kind of coincident that the spreading center, ultra slow spreading center, is generally classified about 2 centimeters a year, and that's the same velocity as the Caribbean plate. So that's an interesting correlation between the velocity of the plate and then also the typical exhumation of this mantle, or these kind of slow spreading ridges. Magnetization is weak for this particular area. There's a similar paper and a similar setting that's been cited in the Indian Ocean. It's also been dredged and has been determined to have exhumed mantle or periddotites on it. And it has a little bit more robust magnetic signature, but I think it's varied, right? So you can have different levels of exhumation and different rates of spreading as well. But I don't know why this keeps on advancing without me doing it. So the seismic characters are pretty similar. I mean, you go from an extensional domain to these listric faults that are bound on either side of these extensional features, and that's what we see in the offshore Columbia area too. And specifically, these fault blocks, as Lutz pointed out in his 2018 paper, these fault blocks decrease in size between these listric faults. And that's exactly what we see here. And I didn't interpret this on purpose, because you can see the larger fault blocks here underneath the label, and how the size of these fault blocks consistently decreases as you move to the left or to the west in Columbia. And this is the Moho here. So then how can we constrain with what we see in seismic with gravity as well? So Lutz did a gravity model for what he saw in the Nansen Basin. And we have the 3D gravity model that Chuck Campbell has performed and created in the deepwater section of Columbia as well. And our values for what we've determined to match with the observed or calculated match through this area of thin oceanic crust. And it gets a little, this is the Beata Ridge. It gets a little weird over here, but I think that has to do generally with the multi generations of flows that are on the Beata Ridge. So our values for seawater agree. Sediments, the ranges generally agree. The oceanic crust is pretty close, and then we've added a lower crust value at 3.05, and the upper mantles at 3.2 for our study, and then Lutz's was 3.25. But I think this upholds the idea that if you have a 3 kilometer thick crust, that has to be a higher density material than your standard 5 to 6 kilometer oceanic crust. And how do you get that? Well, you exhume mantle. And at least internally within ION, I think I've been one of the ones that's resisted any idea of serpentinized periddotites or exhumed mantle, but I think it makes a pretty good case for it here. And what we also see, these are different examples from Reston 2018, Mafion 2013, and then again Lutz, is with this kind of Chapman detachment mode type of spreading, you'll get an asymmetric crustal architecture. And you can see on the map, this is our crustal thickness map in the upper left. You can see that we have an asymmetrical relationship between the shallowing of the Moho in the northeast, and then more of a gradual thinning or shallowing on the Moho in the southwest within this area of thinner crust, or exhumed mantle is what we're calling it. And the total extension generally in this type of setting is attributed to these larger detachments. It's not a your typical spreading ridge, if you will, where you're emplacing basalts or pillow basalts at a spreading ridge. This is essentially a magma absent type of spreading. So then, I talked about this a little bit earlier. Why don't you see any type of magnetic anomaly? Well, this is the Southwest Indian Ridge example that we talked about before. They do confirm the presence of mantle-derived segments at this ocean floor, but they also pointed out that these peridotites in magnetic data lack the magnetization to produce some type of anomaly to be able to map it. And back in 2019, I was sure this has had to be the spreading ridge, but I think it might be just a period of which there actually was a magnetic signature produced, and or because this is a tilt derivative, it might have something to do with the actual structure within that crust. We don't see a strong evidence that there's this anomaly. We can kind of track it through the seismic data, but it doesn't have it doesn't stand out from a seismic character to be able to say it's anything of significant importance within the data. Okay, so age. This is a composite seismic lying all the way from western Panama through Panama to the Colombian border, all the way to the Beata Ridge. So I mentioned earlier that we know that the spreading between or within the plateau occurred because we observed it in Panama. And this is something we presented at that GeoGolf conference as well. We have basically a set of conjugate SDRs across Panama where we pointed out that we think that it spread in a fan-like opening. And these fan-like openings and fan-like spreadings occur at the ridges in the Pacific today. So we think it occurred. This is kind of a recorded history of it as it passed over the Galapagos hotspot in the Pacific. We move into the Emberara Hills. We have SDRs, these inner SDRs that flank the spreading ridge, like we pointed out earlier, up into the plateau and in the Beata Ridge again. So what's the age of this spreading center? And during that transition slide, I showed where we connected to the ODP 999 well and the 153. The ODP 999 is closest to the Emberara Hills on the Kogi Rise, and it has a very distinct signature for the late Miocene. And we know it's been drilled. It's been documented in ODP 999, and we can map it all the way down through the Sinu Prism in the south. And what we can see across the Emberara Hills is the late Miocene clearly extends into Panama. And I'll zoom in on this. But we can see from kind of a regional context, we can see the presence of the late Miocene across the Emberara Hills up until this point, and then the late Miocene, again, drilled and documented from 153 and the other DSDP wells in that area. And we can see it extend across the top of the plateau until about this area. Now, if we zoom in, this is the Emberara Hills in between Panama and Colombia. We see the late Miocene. This is what we see in 099, and we see the late Cretaceous sediments below that on top of basement. And basement's pretty mappable. It's easy to distinguish between basement and the overlying sediments. Now we'll zoom in even further. Again, late Miocene are these kind of chaotic, fractured carbonates that we know from the DSDP reports, and then this really apparent unconformity with subsequent onlap. Now, what we don't see is the continuation of these late Miocene sediments to the east in this section. So I guess what the implications are is that outside of this yellow area, this spreading ridge area, we do see late Miocene. We can map it, but what we can't see is that same seismic character within the spreading ridge or this area of thin oceanic crust. It's just not there. And I understand that there was a consensus that the late Miocene and Cretaceous, they're just, there's drape within these small half grabens and whatnot. But I think now with the recent imaging of the seismic, it's a clear termination of these late Miocene and older units underneath this unconformity. So we would place the age of the spreading post late Miocene. And this is we've bounced ideas like this off of Jim Pindell, Camilo Montes. I think he's on this call as well. And it's not received very well. And there was a consensus that the world was flat for a period of time too, and it wasn't. So we're working with this hypothesis at the moment, and I think what's important is that now that we have kind of a newly imaged and more or highly resolved seismic, we can see the transition from these kind of older units to this more recent late Miocene and onward infill from the Magdalena. And I know that's a controversial interpretation. We're aware of that, but we're proceeding as that is the interpretation as we go. So, so how do you get within the plateau? How do you get 80,000 square kilometers of new crust when you're sandwiched in between the North American plate and the South American plate, if this indeed happened in the late Miocene? So I have a line here that parallels the Hess Escarpment, or nearly parallels it, and it moves up to the Beata Ridge. And going back to the Moho question, how can you map it? Well, we get a pretty good idea of it here, so we can get a good idea of crustal thickness. But something this reprocessing has also done is given us some more insights into the internal crustal architecture within the clip itself and within the plateau. So we can see these dipping beds or dipping reflectors. I guess they're not beds, they're volcanic events within the Beata Ridge area. So then I've taken the same line, I've put it on to the average energy attribute, where you can more clearly make out some of the internal reflectivity within the crust. And what we notice when you look at the sedimentary pile is that this is late Miocene. That's what this kind of bright event is here, but you see it's tilted here as well. So that would indicate, at least for our interpretation is that this section of plateau has been thrusted upon itself at the position of the Beata Ridge in a shortening fashion. And then this has probably been shortened to about 100 kilometers is what we estimate right now. If you restore it, I think that's probably pretty close to accurate. And I think there's other thrusts that are outside of the data that we have that would indicate additional shortening as well within the crust. So that kind of helps. Provide some space, if you will, for that spreading center. And we know that it happened after the late Miocene because these beds are now in this kind of upthrown position compared to their same orientation in the west. So that was a shortening from the north. So how's the interaction with the South American plate? And again, this is a little harder to constrain, but we have some recent publications by Cornwaith. This is a paper that Camilo Montes pointed us to. And I think what's interesting is this area of thin crust, it appears to enter the South Caribbean deformed belt, and the southern limit of it tends to line up with the Oka Fault, which is also where Cornwaith, approximate area where he'd put the tear in the slab. And then to the north, we just don't know. I think Jim has some ideas that it might line up with some of the rotated fault blocks in northern Venezuela. So those are the data points in the south that we would have. And it's trying to understand the transition from the Caribbean plate as it enters into the subduction zone. But I want to point out, I mean, we're not in any way saying that there's some sort of coupling in between the Oka Fault, which is on the South American plate, and what would have been kind of the southern limit of the spreading on the clip, because they're obviously two different plates. But it's just kind of interesting to see that both those line up. And then we also see where you start to have the area of plateau crust again, where here, there's actually even some shortening of the plateau as it enters into the form belt. You can see the basement involved thick skin faulting, pushing back up to the north in this kind of oblique subduction. So yes, if we interpret it as the spreading in the interior and the deep water area of Colombia is late Miocene, what does that do? What are the implications for prospectivity? What's the impact on it? I'll show some AVO results later that would indicate there's probably not an impact, but what it might do is introduce a new play. So the DSTP 154 in the early Pliocene actually had some high TOC units. So they were even range up to 5.9, which is a really robust source rock. So that could be, in fact, what we see is these DHIs in the deep water that could be sourced from this particular interval. So I don't want to forget about certain data points like this, which are pretty crucial. So that's that could be a possibility. So then if we move into the AVOs, this is the similar, the same calculation that we used for on Tara's talk. This is the estimate of the AVO gradient on some of these DHIs that we see in the deep water. This is a line from the Esmeralda area, and you can see these bright amplitudes outside of the South Caribbean deformed belt, this broad MTC or this well-dispersed MTC that Antara referred to earlier. Nice BSR on structure, and it tracks through the deep water here. What we'll do for the series next slides is show the depth, the nears, the fars, then the AVO, and then the velocity as well, similar to what Antara did. So this is the depth stack. These are the nears. That's the 5 to 15 angle, and then the fars. So you can see there's a significant amount of brightening occurring. Amplitude increase as you move to the fars. These are the nears, the fars, and then the AVO attribute. So rather large area of I guess response with this AVO attribute in the deeper section. And then this is the velocity model for that. So you can see a significant velocity inversion within that same package, and also on structure over here. A similar area, this is also near Esmeralda, similar feature, nears, fars, and then the AVO attribute. Again, good results in brightening on structure on these two areas. Velocity model. And sometimes, and this is, this is a little bit different, it only shows marginal velocity inversion on these DHIs. PSDM, and you can see the flat spots and some of the brightening as you move up to structure. Nears, and then fars, nears, fars. You see this flat spot track down through, and then the AVO attribute, and then velocity. So this is from the deep water within that area of thinner crust. And we have these bright amplitude anomalies that I know Miguel has talked about before in the past. Typically, they're associated with the faults that are coming off of the basement in the deep water where the thin crust exists. They come up to these Pleistocene units, and they usually have these kind of stacked DHI responses that we see here. These are nears, fars, so certainly brightening with offset. And then the AVO attribute. So, and I think early this year, maybe December or January, we published an article within GeoXpro where we had Shihong do a standard and AVO analysis, the conditioning of the gathers, and he focused on this area in particular. And these are the results. These are the conditioned gathers. This is the unit. This is again the target that we just saw on that seismic line. Excuse me. These are the conditioned gathers for the seismic. This is the modeled gas and modeled oil gather response for a well of similar depth with a proven gas and then proven oil as well. And this is how it plots on the cross plot. So our target, which is what we which is on the left, falls in between both gas and oil. So we think there's probably a fairly clear case that there's the presence of hydrocarbons within this section of seismic. And I think on the GeoExpert article, we published the cross plot just like this. So then some other features, I only put these in kind of last minute, is similar to Ranger and Guyana. I think there might be a case to say that there's actually these carbonate buildups on volcanic or on these basement these basement highs. So that's just interesting as well. We see this every so often out in the deep water area of Colombia. So then just to kind of wrap up my section, based on analogs and our interpretation of what we see in the data so far, I can make the case that I think what we see in this area of thin crust, because it's thin, it would have to be more dense. And how do you get that, how do you create a thin and dense section of oceanic crust? And that would be basically exhumation of the mantle. And I think the seismic lines up with the models that were put out by Lutz and Reston, where you see, these small blocks of exhumed mantle that are bounded by larger listric faults. And that's how we can interpret the data as well. The age of the spreading is late Miocene, and I'm glad this is an online conference because you guys can't throw tomatoes at me, but that's the way we've interpreted right now based on this really clear and well-defined unconformity that encircles this area of thin crust, and then that age is constrained again by the ODP, DP wells on either side, and the seismic character is just absent of those units. Is absent inside the spreading ridge area. So that's our interpretation for the moment, and I guess we'll gauge on the amount of questions and challenges as to how well it's received. I thank you for coming. Thank you for listening. This is an example of a strike line through what Antara showed, but it shows the variability of these velocity models and the complexity of the margin in offshore Colombia. You get these velocity inversions both at depth and then in the shallow as well. So it's highly complex. It's been a great time interpreting these data. So I appreciate your attendance. That's all I have.
Thank you, Kyle. Thank you, Antara from the ANH. We thank you very much for this really amazing presentation about what's going on into the Caribbean, into the Sinú offshore, Guajira, Magdalena Juan, and into the deep water. So now, if any of the attendees got any question, yeah, there is a question from Camilo Montes. What could be the provenance of the thick upper Miocene section?
Well, I mean, I think it would have to be either the Atrato or the Magdalena. I think based on some of the reading that we've done, and Camilo, this is something that we've talked about in the past, is putting this all into kind of a larger regional context, and that's what we're in the process of doing. But I would think the thick upper Miocene and then the sediments beyond that would be Atrato and Magdalena. And there's a lot going on in the Miocene in this area. You've got the docking of Panama, the initiation of the Magdalena sediments dumping out into the Caribbean as well. So I understand regional context is very significant.
Thank you, Kyle. Is there any other question by the attendees? Well, it seems that at this very moment, we got no further questions. But if any of the attendees maybe are interested into making a further question, or maybe if you're watching this video into the recording afterwards, just write to an email from the ANH, and we'll be happy to direct or to redirect those questions to Kyle and Antara. And again, Kyle and Tara, thank you for this amazing presentation and the amazing job that Ion performed into the whole reprocessing of the Caribbean. That's quite important. And taking into account that Moho and those reflectors into the crust, it's just pretty amazing. So thank you very much, and see you all of the attendees next Friday. Thank you to the Ion team.
Thank you, Danielle. Thanks,
Danny.
everyone.